Hello everyone, and thanks for watching Edupedia World Videos. This is the second lecture of Newton's laws of motion, in which we will discuss Newton's second and third laws, and we'll see how to solve problems involving both inertial frames and non-inertial frames. So let's get into it. Newton's second law of motion states that the net force on a body is equal to the rate of change of its momentum. So this is slightly different from the common version which you might have seen, which is force equals mass times acceleration. So first let's look at the definition of momentum. The momentum of an object is defined as its mass times its velocity. Now this is a vector equation, and the way this really should be written is P equals mv. P is the momentum, which is a vector. V is the velocity, which is a vector, and m is the mass, which is a scalar. So we see that the direction of momentum is the same as the direction of velocity, and its magnitude is equal to the mass times the magnitude of velocity. Right? What momentum really measures is, in a way, it measures the impact or the tendency of a body to change the state of motion. For example, if you get hit by a scooter, right, traveling at a very high speed, it's going to hurt you. But if you get hit by a scooter traveling at a small speed, it might not hurt you that much. But if you get hit by a truck traveling at the same small speed, you might get hurt a little bit more. So we see that your impact is not just related to the speed. Yes, it increases as the speed increases, but for the same speed, the impact is more when a more massive body hits you. Right? So it makes sense to calculate something which quantifies the impact of a body, and it makes sense to make it depend both on the mass and the velocity, because for the same mass, if a body hits you with a greater speed, it hurts more, and for the same speed, if a body hits you with a greater mass, it hurts more. Right? So momentum is this tendency of impacting another thing, and the force is defined as the rate of change of momentum. By the way, whenever we say rate of change, it's implied that it means change with respect to time. Rate, the word is used for change with respect to time. So Newton's second law basically says that the force, again a vector equation, is equal to dP by dt. The instantaneous rate of change of momentum with respect to time is the force acting on a particle. So if dP by dt is 0, that means if the momentum is constant, then the force is 0, right? Makes sense. So let's put the first equation inside the second equation and see what we get. F is equal to d of mv by dt. This is the derivative of two things which are multiplied. So we can use the product rule, which says that the derivative of m into v is m times the derivative of v plus v times the derivative of m. Right? This equals ma. Acceleration is the rate of change of velocity. We've seen that in kinematics. Plus v times dm by dt. And this will be equal to ma, our familiar Newton's second law, if dm by dt, v is not 0, we know that, dm by dt equals 0, which means that m is constant. Now that might seem silly to you. The mass is generally constant, right? And that is true. And for all cases in which the mass of an object remains constant, we can use F is equal to ma, which is what we'll continue using up till we reach a very special point when we'll start talking about variable mass systems. Now when I talk about variable mass systems, I don't mean an object moving and its mass changing randomly with time. A variable mass system could be, for example, a tanker having a lot of water moving, and it has a hole in it in which some water comes out, right? Let's say 1 kg of water comes out every minute. So the mass of this tanker is decreasing with time. So in this case, F is equal to ma will not be valid because dm by dt will not be 0. We'll look at such cases later on. Another case, which is a very common example, is how rockets work. Rockets work by rockets move forward by ejecting fuel. Now the fuel has some mass, so as the rocket keeps on moving, its mass tends to decrease because it keeps ejecting fuel, let's say at the rate of 2 kilograms per minute. So even in rocket systems, we cannot use F is equal to ma, and in both these systems, in these rockets and in these tanks or any other systems in which the mass of the system is changing with time, we will have to use F is equal to dp by dt, that is force is the change in momentum. However, for standard cases, for example, if I am pushing a book, then the mass of the book is not changing with time, and in most such cases we can use F is equal to ma, right? So the force is mass times the acceleration only if the mass is constant, and for the next few videos we will assume that the mass is constant, and you're going to recognize immediately once the mass starts changing. Newton's third law of motion states that for every action there is an equal and opposite reaction. Right, now these have certain properties, so let's look at this in a little bit more detail. Let's say there's an object of mass 5 kg and a man is standing there pushing the object with a force of 100 newtons. Newtons is the general unit of force, and 1 Newton is 1 kilogram multiplied by 1 meter per second square. So it's Newton is the SI unit of force, as we say. So if the man is pushing the block with this force of 100 newtons, then the block pushes the man back with a speed of 100 newtons. If I punch a wall with a force of 10 newtons, then the wall will hit my hand back with a force of 10 newtons. Now, this 100 Newton force is acting on this block by this man. So this force is force acting on block by man. I won't write all this in detail later, but this is a point which generally gives confusion to students. You should be careful of who is applying the force and on whom is the force being applied. In this case, the force is applied on the block by the man, and this 100 Newton's force is applied on the man by the block. Right, we see that both of them have the same magnitude. This force, either one of them could be called the action. If we are talking from the point of view of the man, then this would be called action, the force which the man pushes, and this would be called the reaction. But if we are looking from the point of view of the block, then the second one would be called action and the first one would be called reaction. We see that they have the same magnitude, 100 Newton. They have opposite directions and they act on different bodies. Right. So these are three properties which you need to know. Action and reaction have equal magnitude always. They have opposite directions. They are basically the opposite of each other. If two vectors are the opposite of each other, then they have the same magnitude and their directions are opposite. And the third and most important thing, action and reaction always act on different bodies. Right. So in the first case, in this we saw the action is acting on the block and the reaction is acting on the man. So they will never cancel out. Some students have this erroneous notion that action and reaction are equal and opposite. So the net force will become zero. If I hit a wall, then the net force is not zero because there is one force which I am applying on the wall and there is another force which the wall is applying on me. So the net force will not be zero. Both those forces cannot be added. If you are calculating the force on the man, then the force on the wall will not count and the net force on the man will be minus 100 or whatever. Right. So action and reaction act on different bodies. So let's try to solve a few problems using Newton's laws now. And in this process, we'll see many different forces, but all those forces can be categorized under the four forces which we saw. So this is an object with a mass of 10 kg on the floor. So what is the net force acting on the object? Well, that's easy enough. We don't even need the second law. The object is at rest, so the acceleration of the object is 0. That means the force on the object is equal to 10 times 0 equals 0. Right. So we will always be using F is equal to ma from now on until the time when we reach variable mass systems. But this object has to have a force on it equal to 98 newtons, which is equal to mg, the mass times gravity. By the way, from now on, whenever we take gravity, we'll take it to be 10 meters per second square, just for the sake of simplicity. Gravity is generally 9.8 meters per second square. So m times g will give me 98 newtons, but we'll approximately take it to be 10 meters per second square to make calculation easy. So instead of 98 newtons, let me write this as 100 newtons. So if a 100 Newton force is acting downwards and the net force is 0, then there can be only one conclusion, which is that a 100 Newton's force must be acting upwards. Remember, Newton's law always talk about the net force acting on the body. They don't talk about an individual force. So if an object is at rest, that does not mean that no force is acting on the body. It means that forces may be acting on the body, but the net force will have to be 0. So the sum of all forces will be 0. We can look at it more clearly when we draw a separate illustration of this, which is in technical language referred to as a free body diagram. And this is one of the most important concepts you need to know. And it's not really a concept, but it helps. So every time you need to solve a question involving Newton's laws of motion, I'm going to give, just like I gave you a checklist for what to do in solving problems involving kinematics, such as you decide the two events, you decide which equation to use, you decide which direction to use the equation in, and in which frame you use the equation. I'll give you a checklist of things to do in Newton's laws of motion. And the first thing to do is choose a system. So it might get complicated in later questions, but in this question the system is this 10 kg block. It's easy enough. That is the system on which we are applying F is equal to m, or rather the system which we are analyzing. So, and then we have to draw a free body diagram. So I am going to draw the free body diagram of this 10 kg object. Right. So you draw the object, you write the mass, and you write all the forces acting on the body. Now this is very important. If this 10 kg block applies a force of 100 newtons on a man, we do not include that in the free body diagram of the block. We will include that in the free body diagram of the man. Right? So every force acting on the block is to be included. All the forces acting on the block are to be included, and the forces acting by the block are not to be included. So it has one force of 100 newtons, and it has another force which we will call N. Right, I'll just remove this units so that it won't cause confusion. N is generally the letter which is used for the normal contact force, and it is just another word for the force when two objects are in contact. If I am pushing a block, then I am in contact with the block and I am applying a contact force on the block, and the block is applying a contact force back on me. Right, so the forces by virtue of contact are called contact forces. Normal is another word for perpendicular, and once we reach friction, we'll take care of this exception, but right now we will assume that all contact forces act perpendicular to the surfaces in contact. So in this case, this is the surface in contact. So we will assume that the normal force acts perpendicular to it, not in this direction, not in this direction, but perpendicular to the surfaces in contact. Right? So these two, and then we write the acceleration somewhere along the side. So this is our free body diagram of the man. Generally to denote, to avoid confusion, I put an acceleration in a sort of cloud. So this will be the free body diagram of this object. Now once we've drawn the free, it might seem superfluous to you right now. It might seem that this diagram is pretty much the same as this diagram. It's true in this case, but once we reach more complicated systems, we'll see many differences, and we'll see that the concept of drawing a free body diagram for each separate system reduces the amount of errors. So now we apply F is equal to ma. In this case, it's quite easy. We'll apply it in the y direction, and we can write simply, we can take either direction to be positive, it doesn't matter. If I take upwards to be positive, n minus 100 is equal to 10 into 0. The actual equation we applied is summation F is equal to MA. If you've never seen this, don't worry, this is another symbol for sum. That means we add all the forces. So N will be positive when it's upwards, 100 will be negative because it's downwards, N minus 100 will be equal to the mass, which is 10 times the acceleration, which is 0. So this gives me N equals to 100. So we've calculated this simple problem. We've calculated that the earth attracts the object with a force of 10 Newton, and the surface on which it is, for example, if it's kept on a desk, then the desk pushes it upwards with a force of 100 newtons. Right? Let's expand on this question. (10 kg). Let's say I'm applying a force of 40 newtons. This is me applying a force of 40 newtons. Then what is the normal contact force? So we'll do the same thing. We'll draw a free body diagram. A force of mg, that is 100, is acting downwards. We know a force of 40 is acting upwards because I'm applying it. And a force N must be acting. And the acceleration again is 0. Right? So we can write N plus 40 minus 100 is equal to 10 into 0, which gives me N equals 60. Right? Easy enough. Now what if this, instead of 40, was 120? Then our equation would be N plus 120 minus 100 is equal to 10 into 0, which would give me N equal to minus 20. That means the table would be attracting downwards the block with a force of 20 newtons. But this is not possible. And this is another property of the normal contact force. We saw one property of the normal contact force, that it is always perpendicular to the surfaces in contact. The second property is that the normal contact force always pushes, never pulls. So, and we can see that as well. If we apply a force greater than 100 Newton, there is nothing to stop the object from going up, right? Unless it's stapled or is nailed down to the desk. So the normal force will always push the body, and its minimum value could be 0. So in this question, what will happen is, the free body diagram would be like this. 100, we know 120 Newton is acting, and the normal force will not act. In fact, another way to see this is, normal contact force is the force by virtue of contact, right? The moment the block rises even 1 millimeter up, it's not in contact with the ground anymore, so the normal force becomes 0, right? So the normal force will be 0, and we don't know the acceleration, but we know it will accelerate upwards. So in the cloud, I just draw an acceleration of A upwards. Now we could take any direction to be positive. Let's take upward to be positive. The equation becomes 120 minus 100 is equal to 10 into A, which gives me 20 is equal to 10A, which gives me A equals 2 meter per second square. So when I was not applying any force, the normal was 100. When I was applying a force of 40 Newton, the normal became 60 Newtons. When I'm applying a force of 99 Newtons, the normal will become 1 Newton. But when I'll apply the force of 101 Newton, the normal will not become minus 1. It will become 0 and the object will start going upwards. Right? So this is a property of the normal force. Now I'm going to show you another new type of force, which is called tension. These are forces by ropes. They can also be by rods. And their property, right now we'll just focus on ropes. We'll look at rods later on. So ropes, their property is the opposite of normal. They can only pull, never push. And what I mean by that is, let's say there's a block of 1 kg and I am standing here and a rope is attached and the rope is connected between the block and me. If I pull the rope towards myself, the block will move towards right. Right? That means the rope will apply a force towards itself on the block. It will pull. But what if I try to push the rope? Can I push this block by pushing the rope? No, because then the rope will just slack like this and I won't be able to apply any tension. Right? However, if I, instead of attaching the block to a rope, I attached it to a rod, then I could pull the rod and the block would come towards me. I could push the rod and the block would go away from me. So the normal force can only push, the tension can only pull. And forces by rods can either push or pull. And when they push, we call it the normal force, and when they pull, we call it the tension. Right? So let's try to solve some problems involving tension. There's a block of mass 10 kg and it is hanging from a ceiling by a rope. Right? The mass of the rope is equal to 4 kg. So we want the force on the block due to the rope. So the first step now is we choose our system. Keep in mind, we could choose anything to be our system as long as there's a particular constraint for us. The acceleration of the net system will have to be the same. So for example, I could choose this block to be my system, or I could choose this block and this rope complete to be my system, or I could choose this block and half of this rope to be my system. I can choose anything to be my system. Or for example, if there are 3 blocks attached to ropes and I'm pulling those and all those 3 blocks are moving towards right with an acceleration of 2. I can take the first block to be my system, I can take the second to be my system, I can take the third to be my system, I can take the first 2 to be my system, I can take the second 2 to be my system, or I can take all 3 of them to be my system. Right? If there's an object moving with an acceleration of 2 and another object moving with an acceleration of 1, I cannot take these combined as a system. I might be able to do them later on, but for now we can only take systems in which all the parts have the same acceleration. And it should make sense to you, because the moment I take the acceleration to be 2 and to be 1, once I write F is equal to ma, what am I going to take A to be? A is different, but if all of them has the same acceleration, that will be the acceleration in ma, and m will be the sum of all the masses. Right? So if we take this system to be an object in which one part has 3 meters per second square, the other part is 4 meters per second square, we can't really write the net acceleration of the system. But if every part of the system has 1 meter per second square, we can say the acceleration of the system is 1 meter per second square. If this seems a little abstract to you, just think of it like this way. If we have a 10 kg object, it is actually comprised of a million systems, right, of small masses each. We can take each atom to be a system. We can take a fourth of this to be one system. We can take the whole thing to be one system. Every part has the same acceleration a towards right. Right? So we could take the whole thing as a system. We didn't say we have to take only a particle as a system. So as long as every part of the system has the same acceleration, we can take them as a system. Right? So let's look at this again. (10 kg object, mass of the rope is 4 kg. We'll assume that the mass is uniformly distributed. So for example, half the rope weighs 2 kg and a quarter of the rope weighs 1 kg. We want to find out the force on the block due to rope. Since we need to find out the force on the block, it makes sense to choose the block as the system. So we choose the block as a system and draw an FBD for it. FBD is just a short form of free body diagram. So mass is 10. A force of 100 Newton is acting downwards. This is mg. We'll always put mg if the experiment is happening on Earth. And we'll say T. Just like N is the symbol used for normal, T is the symbol used for tension. And we'll take T upwards, and in a cloud I'll write the acceleration, which in this case is 0. So it gives me T minus 100 equals 0, or T is equal to 100. Let's say I was asked the force on the rope due to the ceiling. So that means I am asked this force. So it makes sense for me to choose the rope as the system, right? So I'm just going to draw it as a block because that's generally the habit which we should develop, but it's the rope in this case. So this is the free body diagram of the block. Now I'm going to draw the free body diagram of the rope. The mass is 4 kg, so 40 newtons is acting downwards, which is mg. We can't call it T because we use T here, so let's call it T1. And the acceleration is 0. So can we say T1 is equal to 40? No, we cannot. That would give us an error. And the reason that would give us an error is because yes, we have included forces acting on the block, acting on the rope, but we've not included all the forces acting on the rope. So think of it this way. Every action has to have an equal and opposite reaction, right? What is the reaction of this 100 Newton force? This 100 Newton force is applied on this block by the earth. So if this is the earth and this is the block, the 100 Newton force is applied by the earth on the block. The reaction will be the earth is pulled upwards by a 100 Newton force by the block, and that's true. If I keep an apple at a certain height, the earth attracts the apple and the apple attracts the earth with the same force, right? G m1 m2 by r squared. So the reaction of this 100 Newton force is this 100 Newton force acting upwards on the earth. If we ever try to choose the earth as our system, then we would need to take this 100 Newton force, but right now we don't. This T is the force acting by this rope on this block. It has to have a reaction. The reaction will be the force acting on the rope by the block. And we've seen properties of action and reaction. They're equal and opposite and act on different bodies. So if the rope has a force of 100 Newton upwards on the block applies a force T of 100 Newton downwards on the rope. So, and this is basically, you can see it like this. This T is applied on this block by this rope. The reaction, this T is applied on this rope by this block by this rope, and that's actually what makes the rope stretch. If there was no block, the rope would not have stretched. It might have slacked a little bit, but the rope will be completely stretched if we apply a heavy block towards it. So we have to take this T in as well, and now I'll get T1 minus T minus 40 is equal to 4 into 0. T is equal to 100. We've already calculated. So T1 is equal to 140. Right? But I could have done it in a much easier way actually. I could have been a little tricky and I could have taken this whole thing to be a system. Now how does that work? How do we take this whole thing to be a system? Can we take this to be a system? First of all, yes we can, because the acceleration of both the particles is 0. If the rope had an acceleration but the block did not, we could not take the whole thing as a system. So the whole thing has a mass of 14 kg. That means it has 140 newtons acting downwards, mg. And now what about this T? Now we do not need to consider this T anymore because it becomes an internal force. Right? Let's say I have a block, then the internal molecules of the block do attract each other and they do put action and reaction forces on each other. But if we take the complete block as the system, they cancel. Right? Look at it this way. I have this block. Right, so there's this molecule and this molecule. This attracts this with the force F. This attracts this with the force F. When I'm taking the block as a system, these two forces add up to 0. If I took only this molecule as a system, then they would not be 0. But if I take the whole block as a system, the internal forces add up to 0. So if I take this rope and this block to be the complete mass combined system, then these T would be internal forces. If you wanted to be really specific, you could add both of them and still get 0. But we generally don't write internal forces on a free body diagram. So, and we get T1 up. And obviously in the cloud, I write the acceleration is 0. So we get T1 is equal to 140 again. Right? Now, let me ask you a trickier question and let's see if you can, the whole trick will be deciding the system. Same question. 10 kg's mass is 4. We saw that at the top, the tension in the rope was 140 newtons and at the bottom it was 100 newtons. So the tension in the rope is not the same throughout. Right? So if I ask you what is the tension at the middle point of the rope, you could do it in 100 different ways. You could take this to be a system. You could take this to be a system. You could take this combined to be a system. And from experience, I can tell you taking this combined thing to be a system will be nice. So let's do that. So the combined mass of the system is 12 kg. It'll have 120 acting downwards and it'll have, let's say, T2 acting upwards. Is there any other force acting? No. We do not need to take this force now because this is the system. So T1 and T1 will be acting here. If we took the complete thing as a system, these would add up to 0. But then we would not be able to calculate T1. So we take this as a system and, this should be T2. And we can calculate T2 equals 120 Newton. And now I think you can see the pattern. Here the tension is 100. Here it's 110, 120, 130, 140. Right? The last important concept. A lot of time you'll be given a light rope. Light is just another code word for mass is 0. Right? So whenever we say a block is attached to a light rope, it means that the mass of the rope is 0. And unless I mention otherwise, we'll assume that the ropes are right. So unless I specifically give you the mass of the rope, you can assume the rope to be light. And the properties of a light rope are the tension is the same throughout. So if this M was 0, then all of these would have a force, a tension of 100 newtons each. You can see that directly or you can try to calculate it again. So when we are given light ropes, we can just take the tension in the rope to be T and it will be the tension at every point. Let's take one last question. (10 kg block). I apply a force of 100 newtons at an angle of 37 degrees. What is the acceleration of the particle? So what we'll do is the first thing we draw the free body diagram. 10, 100 must be acting downwards. There must be a normal acting upwards. We don't know how much it is. And there's a force acting 100 newtons at 37 degrees. Right, so this is one level above the questions we've seen so far. In the questions we saw so far, all the forces are acting along a straight line, so we only needed one equation. Now these forces are acting along a plane, so we'll need two equations. Right, so what we'll do is, we'll resolve all the motion into two perpendicular directions. Let's take these two directions. So 100 can be resolved into two components. So I'll write the two components. This would be 100 sine 37. That would be 60 and 100 cos 37 would be 80. If you don't remember, 37, 53 are the angles of a 3, 4, 5 triangle. So you need to remember these values. Right. So now we can write the equations in two separate directions. For the vertical direction, let's do the horizontal direction first. The horizontal direction is easy enough. There's a force of 80 newtons acting. And that's it. That's the only force. So 80 is equal to 10 into A. That gives me A equals 8 meter per second square. The acceleration is not complete yet. We only know the horizontal acceleration. That is 8. Is there a vertical acceleration? Let's see. This is n, this is 60, this is 100. Right. So n can come out to be 40, giving the vertical acceleration to be 0. So the net acceleration will be 8 meters per second square. But what if this, instead of being 100, this was 200? Then this would have been 160 and this would have been 120. In that case, yes, the acceleration horizontal would have been 16 meters per second square, but the vertical direction would have 100 downwards, 120 upwards, and now you cannot have n downwards. Remember, n can't pull. So now the acceleration upwards would be 120 minus 100 is 20, divided by the mass is 2, so it would be 2. So if it's 100, the acceleration is 8 towards the right, but if it's 200, the acceleration has two components. It is 16 towards the right and 2 vertically, and the net acceleration would be root of 2 square plus 16 square, and it would make an angle of tan inverse 2 by 16, and you know all of that. Right? So this is the way you solve problems of motion, Newton's laws. Right? So the things to keep in mind, and we are going to take another lecture to try to just solve problems so you will be more comfortable. But right now you just need to follow these steps, and that will reduce your number of errors. The first step is to choose a system. Currently, we can only handle systems in which all parts have the same acceleration, that is the same magnitude and direction. We'll change this later on. Make a free body diagram. only forces acting on the system are to be considered, all the forces acting on the system are to be considered, and no forces applied by the system are to be considered. Resolve into two perpendicular directions and use F is equal to ma along each direction. Right? Remember, F is equal to ma is valid for any system along any direction and in any frame. Now what do we mean by in any frame? Up till now I've told you that F is equal to ma is valid only for inertial frames, right? But Newton's laws are so helpful and they're so valuable that we would like to use them or their terminology even when we are dealing with non-inertial frames of reference. So we can do that by a small concept, and a very interesting concept called the concept of pseudo forces. Pseudo is another word for false. The pseudo forces are forces which are not really there but which seem to us to be there, right? So let's take an object which has a mass m, and let's say there are lots of forces acting on it. F1, I'm going to do the general case right now, F2, F3, F4, and the acceleration of the object is a in this particular direction, right? So we can write F1 plus F2 plus F3 plus F4 is equal to ma. By the way, when we resolve into two perpendicular directions, we do this only. We write this equation and we'll take all, if these two vectors, if the sum of the four vectors on the LHS and mass times the acceleration on the RHS, if these two vectors are the same, then their x components are the same and their y components are the same. That's what we do when we resolve. Right? Now let's say I do this very same experiment, but I do it with respect to another frame which is moving with an acceleration of a frame. This is all in an inertial frame. And let's say I have a non-inertial frame moving with an acceleration a frame. Then I can use the concept of relative motion. Let's call this frame S. So the acceleration of m relative to s will be the acceleration of m minus the acceleration of s, right? So that will be a minus af, right? So in this equation, my equation, if I were to write the equation in this frame, RHS would give me m times a minus af, right? But LHS would be the sum of all the forces, so that would be F1 plus F2 plus F3 plus F4. Now this is a correct equation and this is a wrong equation, right? We know that. But there is a very small thing we can do to make it correct. Since this equation is true, we can do minus MAF on the LHS as well. So if we do minus MAF, now we know this whole thing is equal to MA minus MAF is equal to M times AF. So now this becomes a correct equation. So we see that we can actually apply the concepts of laws of motion in non-inertial frames and get the correct result if we make this minor adjustment. If to the forces acting on the particle we add one extra force which is equal to minus MAF. So the pseudo force is equal to minus MAF, which is minus mass of the object, the acceleration of the frame. This is important. This is not the mass of the frame. This is not the acceleration of the object. Pseudo force is mass of the object, acceleration of the frame. And this gives us the correct result. We'll apply it in many questions in the next lecture. It might seem a little abstract to you right now. Let me just do it in one question and then show it to you. Oh, sorry. So we have an object 10 kg. Let's do the same question. I'm applying a force of 100 newtons at an angle of 37 degrees. We know that it moves towards right with an acceleration of 8 meters per second square. Let's say I do it in a frame which moves towards the right with an acceleration of 2 meters per second square. So relative to this frame, the acceleration would be 6 meters per second square, right? I can take care of that by applying another force of 20 in this direction. So you apply another force of 20 in this direction and the acceleration will come out to be 100 cos 37, that is 80, minus 20, that is 60. So A will come out to be 60 meter per second square. Right. So you can calculate, you can apply F is equal to ma in an inertial frame and get the answer, or you can apply it in any non-inertial frame as long as you subtract the mass multiplied by the acceleration of the frame in the list of forces. If it's still a little bit abstract to you, we'll look at it concretely in the next video, in which all we'll do is solve problems. Right, we'll take many different cases of problems involving springs and pulleys and inclined planes, the types of problems which you see in your exercises and exams, and we'll try to solve them using the concepts you learned till now. So pseudo forces help us to make Newton's laws even in non-inertial frames by making just one adjustment, which is that we add another force, the negative of the mass, times the acceleration of the frame. Right?